Hello, good afternoon, everybody. Warm welcome. Today. Before we begin, so two parts of today's lecture, maybe this way. So first, a few more comments about interfacing sensors to microcontroller. Just a few because we haven't finished a few slides here. So before we proceed, a few slides about it, and then we move towards digital signal controllers. So, special subcategory of microcontrollers. I would like us to feel the difference between microcontrollers and DSPs. So where the DSCs are positioned and what are their basic operation areas. We'll talk about it. Yet before we continue, next week, of course, we have no lecture. We have a trip. So I don't know if we started one or something, so I'm not really sure yet, but we shall be starting right after the lecture. So of course, it's a bit of a nonsense. To have a remote lecture and right after lecture, then within 5 minutes to be in the bus. So, of course, we can have the lecture in a bus already, if you want. But that's on the way to Prague. So, no lecture next week, at least no lecture remotely. So, we can have it in a bus or then in the evening. In the hotel. Okay, any questions? Maybe. Can you? Yes, you can record me in a bus. Yet the problem will be with presentations, PowerPoint presentations. You know. Okay, let's go then. A few remarks about last week, about the interfacing of the sensors of microcontroller. So normally when we talk about the sensors, we are interested, in case of the sensors, we are interested in having the signals as low noise as possible. Yeah, because we talk here about the analog connection, not digital one, because we talked about it. So when we have this kind of circuitry with differential driver of the or in general with using of a driver, and then when we use a driver, the first elements that are used to deliver a better quality signal or a signal at lower noise are those anti-alias filters. Of course, their basic functionality is to protect against winding the signal back to our baseband. But of course, we can make them here, we can improve the filters, we can make them lower noise, a lower bandwidth. We can narrow their bandwidth to reduce the noises incoming into the ADC. This is a kind of important element. This is kind of important element because the ADCs, especially in microcontrollers that we have now, they tend to have very nice and very fine resolution. So quite often we talk about 12-bit, and more often we talk about 16-bit. 16-bit ADCs with pretty decent bandwidth, so about 2, 3, 4 megahertz sometimes, which means that from one perspective that's great because we can try to sample not only low frequency sensors, but we can try to sample some higher frequency signals. But at the same time, if we are using this kind of high resolution and high bandwidth ADC for low frequency sensors, then we end up with a lot of actually unnecessary noise being transferred into digital domain. Here we have the color of the noise, depending on the spectral density, because that's what we do. That's how we estimate the noise. So the problem is that this is a white noise. So this color is a white. The blue noise here and the violet noise is actually not really physical. In case of physics, we usually have a white noise, pink noise, or red noise. In case of the spectral density, although usually we've got white, which is infinite bandwidth, or gray, which has some finite bandwidth. Still, it's pretty flat. Flat noise means, so flat spectral density means that that if we limit the bandwidth of such a sensor, of the signal coming from such a sensor, then we will see the improvement in the signal to noise ratio, and we will be able to get closer to nominal resolution of the ADC converter that we have implemented in the onto the microcontroller unit. The scale is, so yeah, we don't have much time about going into theory, but the reduction is with the square root of bandwidth, basically, because the SNR is there is such a dependence that signal to noise ratio is inversely proportional to the square root of the bandwidth. So the narrower is the bandwidth we have, the larger SNR we can have. So the higher is the quality we can have, and it's for this reason. So we can improve the SNR, or we can reduce the bandwidth. First of all, with this anti-alias filters, so the input filters to the ADC converter, and then when we have the signal digitally, then we can try to add some signal processing. So the thing that we'll talk about more in a moment. But we can use the signal processing capabilities of microcontrollers that we have today to improve the quality of the signal coming from the ADC converter, or from the digital signals. To give you the idea how much the averaging and the filtering, so the narrowing of the bandwidth, can improve the SNR, I've got a couple of slides. So let's consider we've got the sensor output. So here we have 5 millivolts, 5 millivolt scale. So the amplitude here is about 20 millivolts, and with an averaging of 10 samples, just such a simple averaging. Averaging is nothing else but a low pass filter. Here on the oscilloscope, so I had the samples just from the oscilloscope, so to have it simple, but the same rules apply for a microcontroller as well. So 10 sample averaging is very simple averaging. So you take 10 samples and make an average of it. Reduces the noises already to the level of less than 5 millivolts. Then doing low pass filtering, we get similar amplitude of the noises, but at lower bandwidth. So as we can see, different frequency characteristics of the noises. Better or worse, it's really tough to say. So this is this is something that you need to always adapt to the needs and to the sensor that you are servicing, that you have connected, and to particular requirements of the final user of your device. And here you can see even greater averaging. So 64 sample averaging. About the averaging, yeah, we could quite long about it, yet I would like to just make one last comment about the averaging, because theoretically, as you can see, there is a gain from no averaging between 10 sample and 64 sample averaging, so there is a really significant difference. Yet there is naturally a physical limit, the limit coming from the resolution of the ADC conversion, because theoretically you can try to cheat. So you can try to cheat the resolution, try to artificially increase the resolution by improving increasing the number of samples in the sample averaging, or the strength of the low-pass filter with the low-pass filtering. Yet we always get down to the resolution of the ADC conversion, which means that these filters, where is this line? Yeah, that those filters, this analog fit on the analog side, and the quality of the analog side is definitely non-negligible. Which means that when you are interfacing sensors to a microcontroller, proper signal conditioning is vital. So it's not that you can connect a sensor directly to a microcontroller and utilize 1/10 or 100 of the ADC resolution, and then everything else do by signal processing. It's not true. So don't believe that if anybody says so, or wants to convince you to this view. It's not true. So the good quality starts with the good quality of the analog part, of low noise analog part, and of good anti-alias filtering, and of adapting the signal range, the sensor range to the input range of the ADC, so to utilize the most of the ADC that we can have. Only when this condition is met, only when we are optimal on the analog side, and we can try to add some digital tricks. But the digital tricks are working always together with analog. So it's not that, it's never this, that the digital world will cover completely, or will eat up, or will replace the analog. That's not true. So first the analog, then the digital. It's always working in pairs. So that's my small hint, small maybe warning even, and not to neglect the analog part in case of the sensors. It's also the reason why analog sensors are not that bad, because in case of digital sensors, somebody did it for us and did it in a universal way. If we want to squeeze the most out of the sensors with analog circuitry, we can do it. With digital, not really. So we just get what we pay for, and we can't really squeeze more. So digital filtering, okay, it works. It's really a fantastic thing. We'll talk about it in a moment, although you should be experts after the DSP course, I hope, at least. But anyway, it's not gonna replace a good and clean power supply and good and clean analog part. Okay, let's go further. Not very far from this interfacing of sensors. So we have the sensors interfaced to a microcontroller. But then, what can we do with the signals, or which tools can we use? In case of sensors that are slow, we can use any microcontroller. Yet, if there are a lot of sensors, or if the required bandwidth is not that slow, or if we need to make some special tricks, like synchronous, for example, synchronous detection or wideband detection, then simple microcontrollers are not enough. Then for those purposes, we've got a couple of tools in our portfolio. The most important tools for years have been digital signal processors. Digital signal processors with their special capabilities about processing signals. You did have a course about DSPs, if I'm not mistaken, so we will not be repeating this, of course, very much, but I would like us to just pinpoint or remind you about the major features of DSP, so that we go to the category that I would like us to stop for a short while, to digital signal controllers. So to something that is straddling between MCU and DSP world. We have really nice options here today, and it's not only about Cortex-M7, although Cortex-M7 is a very good example of a DSC. So today, DSPs and DSCs. We start with DSPs, so the basic features, and then digital signal controllers. We will not repeat again about Cortex-M4F, M7 and 33 and 55, as those were already analyzed during the lecture. Yet I would like you to show two side families, two families that are still available, still interesting, completely different from Cortex, existing before Cortex in the world, with some examples of their, with some use cases of those, of the digital signal controllers in general. Digital signal processing, should be pretty obvious to you, or very obvious. So it's application of mathematical operations to digitally represented signals. So we have a sequence of samples obtained from physical signals, like, for example, microphones, various kinds, or ADC converters, or sensors with digital output. And then by the digital signal processor then exactly processes the signal, the stream of data in a digital way. So digital signal processor, then the output can be either a parameter of the signal. So when we need to extract a parameter of such a signal, because those signals can also be a multidimensional signals, like signals from matrices, because they don't have to be single dimensional signals. So we can have signals from cameras, and then we can have the output as an extracted feature of such a signal, like a frequency, for example, frequency characteristic, or an amplitude just, or we can have the output as another stream of data, like, for example, we have an input coming from digital audio, and the output being a digital audio with some modified parameters of the signal. So that's how it can be. Digital signal processor is that, of course, the electronic signal that processes digital signals. DSP is dated, you should remember this from the ITM course, is dated to the same time that original Intel 4003. So it's 1970s by Texas Instruments. So the first DSP, although then the DSP itself was used. The microcontroller is dated then, and the DSP is slightly later, still by the Texas Instruments. In case of DSP tasks, they require general a couple of things to process the signals effectively. So of course those requirements are coming from the character of the operations of the DSP. So there should be, the DSPs themselves should have repetitive numeric computations, should be able to repetitive numeric computation, should be optimized to deliver such a performance, because that's what is critical in DSPs. And naturally, there should be attention to numerical fidelity as well, so that we don't lose the precision during the operations, various operations on the signal stream or stream of data. It should be high memory bandwidth available. When we talk about large amounts of data, large streams of data, especially video data, then the bandwidth of the processor, available bandwidth of writing, reading from memory or from various locations should be pretty high. And the processing should be in real time, because when we are talking about the signals, real time here means two things. First of all, that it should be reliable. Here is the real-time requirement, which means that the processing time should be fairly constant from sample to sample, or from day to day, or from month to month. It should not depend on all the tasks being done by the processor, but that's one thing. Another thing is that the time by real time here means the processor is processing the samples in a short time, short as possible, or in short as available, which means that we have the data processed within around microseconds and milliseconds. Yet, so the real time has two meanings, two slightly different things, as you know. So the processing time should be constant, fairly constant, and rather short. Yeah, that's not important. Common applications of the DSP. Yeah, there are many today. We have many digital streams around us, so of course, plenty of application fields. So I know that you are very much aware of it. So just to tidy the thing, so, or maybe there is somebody that's not remembering, so that communications, various kinds of filtering, modulations, the modulations, of course, audio video processing, graphics, various kinds 2D, 3D graphics, navigation around our GPS, plus the various things like machine vision, guidance problems, control problems, so all the things. So plenty of various applications we have today for signal processing, because the world is digital. In case of algorithms, again, we could think about hundreds of algorithms. 3 of them I put on the list. So for the filtering, the Fourier, so the operations in the frequency domain, signal correlation. So just name just a few. Again, something that you should be very, very well aware of. The filtering algorithm, which is actually nothing else like multiply and accumulate. And then we come to a very important element of digital signal processing. And then going down to microcontrollers, forming the digital signal controllers, is that the major operation available in microcontrollers, in a DSP-aware microcontrollers, or in digital signal controllers, in other words, is a single cycle, or very fast or optimized multiply and accumulate integer and or fractional, integer, fractional, and or floating, because these are 3 different types of operations available. In some microcontrollers, in some DSPs, we've got all 3 types, so support for integer math, fractional math, and floating point math. Sometimes we've got just integer math. So sometimes we've got integer and fractional available, but floating point math not available. So it really depends from DSP and DSC one to another. So these are very important elements, of course, additionally to the MAC operation. There is necessary standard multiplication and standard division. So, of course, not mentioning adding and subtracting, but I think it's obvious that we need this trivial operations for the for processing digital signals. In case of the DSP architecture, the basic architecture is usually has split. So the the beginnings, the originals were in case of the DSP architecture, usually it has a split buses architecture. Split buses are done to increase the memory bandwidth. So that's why from early days of DSP processors, it was more or less this kind of architecture utilized, so with separate program memory and separate data memory. Additionally, in order to increase this memory bandwidth and the access, we've got by default in DSP processors, there is always some DMA. There is always some DMA. The DMA plays a crucial role in offloading a microcontroller from transferring stupid transferring data between peripheral and memories, or memories and memories, or memories and peripherals. Additionally, we've got that's also quite a standard setup in a DSP, or should be, for real-time processing. There is because this is necessary for real-time processing, is the existence of arithmetic circuitry, strong arithmetic circuitry. So besides standard arithmetic logic unit, usually we can expect in signal processors some extra multipliers, some extra integer floating point blocks as well, barrel shifters. These are as well the kind of multipliers slash dividers. And for the same purpose of improving the performance of the DSP itself, not unusual are caches. Not unusual here, just instruction cache, but the data cache is not something something present quite often in microcontrollers. So summing up, the fast data access is done by high bandwidth memory architectures usually, so two usually separate buses. We've got direct memory access. What was not visible on the previous slide, and which is pretty often available, are specialized addressing modes. About the specialized addressing modes in a moment, because there are a couple of addressing modes really extra available here in various DSPs and smaller DSCs. About the addressing modes, as I mentioned, they play an important role. About them in a moment. In case of the fast computations, we've got naturally the multiple mathematical units usually. So Mach-centered, which means that there are special units for making them multiply and accumulate them as a single cycle operation, or in a highly optimized way. That's usually what we have. Then we've got very often the pipelining. The pipelining is increasing the resolution, the performance of our operations. We're talking about it a few lectures before. So that's also usually a standard way of increasing the performance of signal processing unit. And an extra thing is a parallel or superscalar architecture. Various ideas here are utilized. So the two major ones are very long instruction words and single instruction working on multiple data. In general, in case of microcontrollers, for signal processing, the idea about the very long instruction word is to that it's used instead of cache or at the same time with cache. But the idea is to have here, for example, 256-bit wide bus, and take, in order to speed up the access, the reading of the data, of the of instructions from the program memory. Because in other words, we read a couple of instructions in one reading cycle, then reducing the need for the instruction cache and or reducing the latency in accessing the program memory. That's very long instruction word. In case of SIMD idea, this is about using single instruction from program memory, working on multiple, on a batch of data coming from the data memory, they are the mechanism for increasing in general the computation used in signal processing unit. Then we've got wider accumulators, registers as well. Such an idea is in DSPs. So to increase the precision. So for example, instead in a 32-bit microcontrollers, we've got 40-bit accumulators. In 16-bit, we've got 20-bit accumulators, for example. And there is extra features we can expect of special instructions for especially for increasing the performance during the execution of loops. These are so-called zero overhead loops and special repeat instructions. And the idea of shadow register sometimes is somewhere. In some units, signal processing units, we can find such an idea for faster interrupt servicing, so that we don't need to push and pop from stack, push to stack and pop from stack, but then we can simply use shadow registers for the purpose of fast interrupt routine. So a couple of factors, a couple of ideas here that are characterizing or speeding up the execution, the data processing in microcontrollers. Which of these are basically implemented? Oh, special addressing modes. So we will not get through each of them, as I think they are pretty simple. Yet, in case of specialized addressing modes, here, you know, in classic microcontrollers, in general, the idea is to simplify the instruction list, simplify instruction decoder to make the instruction decoder simpler and cheaper. Yet, for signal processing, sometimes we have to go the other way around. Sometimes, for certain algorithms, it's a good idea to have a support of addressing special addressing modes. And one of such an algorithm is an FFT, where with all these butterfly tape operations butterfly tape operations like this one. So then a bit reversal addressing, for example, does the job. In case of classic signal processing, then a very nice addressing idea is the, for example, a circular buffer, this kind of addressing where we can automatically access certain cells with a certain offset, or the addressing with automatic incrementation and or decrementation post and prep. These kind of addressing modes are not usually available in standard microcontrollers. Yet that's one of the important difference between signal processing capable microcontrollers and the standard microcontrollers, so that such processors are having such modes, and then when you have to make the FFT, then the difference is really substantial, because instead of calculating this big special addressing, butterfly tape addressing necessary for FFT, we just simply address, use the hardware support in this domain, and have it in a simple way, have it delivered in a simple way. So then that's a special feature, a very nice one in many situations. In case of signal processing, of course. Okay. Oh, numerical fidelity, maybe the last thing. In case of numerical fidelity, one important remark, again, something from ITM. While we're talking about the differences between fixed point and floating point, but here is a very nice comparison of the dynamic range in case of the values. So in case there are fixed points, so the largest value to the smallest value, 20 logarithms of this ratio for the 32-bit fixed point is 180 decibels, but for a 32-bit floating point it's 1500. So that's the difference. But why to use floating points in signal processing, and how much more the floating points are giving us compared to the fixed point. So it's usually this. So it's usually noticeable in case of signal processing, this dynamic range difference. That's why in case of fixed point processing, so if you want to make fixed point if you are forced to make a fixed point for 32-bit floating, you need to use 64-bit fixed point, a fractional number. So then the resolution, the dynamic range is comparable. 64-bit fixed point is slightly better than 32-bit float, but still it's more comparable than those two values. The highest precision in standard with standard numbers, with standard arithmetics, is dual precision floating point, the use of it. So then the fidelity is the greatest. We receive, yet of course the price we pay in case of memory, in case of processing required is the highest. And then some examples. So yeah, first of all, about the DSP, what to expect from a DSP. Just to show you what can we get if we are patient enough and if we have enough money. Texas Instruments, the Keystone 2 combination of a DSP and an ARM core, the 5.6 gigahertz processing of ARM and 9.6 gigahertz processing of DSP, with the raw computational performance. So that's what we can get of 38 gigamax. So billions of multiplane accumulated instructions per core, and up to 19 billions of floating point operations per core, which means how many filters can we do on such a single unit. Of course, a lot of memory, so that's not maybe that important. Plenty of communication resources, especially because this kind of processors are quite often used in various routers or various network equipment. That's one of their major use case. Of course, the DMA, plenty of things. The architecture you can see here in the slide. So surprisingly, plenty of simple interfaces, but then gigabit Ethernet coprocessor on board, plus quad-core Cortex A15, plus octal core pack with plenty of cache per each core. Take a look per each core. So each core has a lot of cache on board with the DSP pack, because these are the DSP units. This is just for control. So this is the workhorse in this DSP, delivering us such a fantastic performance. But yet, let's put this aside, as this is kind of a lollipop that we are not able to reach. normally, and we will not be playing with it normally. Yet something that will be playing normally, and something that is really used at everyday basis, are the simplified DSPs, which we call DSCs. Historically speaking, the digital signal controllers were simplified DSPs. So yeah, first there was a microprocessor, microcontroller, and then DSP, simple DSPs. Then the DSPs were being improved. So during the whole 1980s, especially Texas Instruments and some analog devices as well, some other companies were delivering to the market more and more sophisticated DSPs, incorporating more and more of those features that we're talking about a few minutes ago. But then it turned out that the DSPs became too complex and difficult to be used. Very often they required assembly processing, plus they did not include any peripherals for HMI, for human machine interfacing, which meant that those DSPs usually required extra processor used for configuration and transferring configuration data between the DSP and the final and the human being. I put it this way. For this reason, of course, the market didn't like it very much, especially for medium and low complexity signal processing. And for those reasons, those DSPs were actually simplified a bit, or they were added. They were simplified, and they started to include more and more peripherals. From the other perspective, the microcontrollers were geared with signal processing capabilities. So in microcontrollers, they were delivered microcontrollers in the market with multiply and accumulate instructions, with special addressing modes, with cache, with DMA. So they started to appear. So two paths were taken: simplifying DSPs and the improving the microcontrollers. I would say that the path of improving the microcontrollers won, especially with such beautiful examples of digital signal controllers like Cortex-M4F and especially Cortex-M7, where plenty of TICs are available, are present from signal processing capabilities. Yet they are not the only examples of this path, of this microcontrollers being transferred towards digital signal controller domain. Those examples, two other families, interesting ones. We'll talk about this during next hour. So let's have 15 minutes break, and after the break, we'll get back to this subject. welcome back after the break. So, examples. What options do we have in case of signal processing? Comparing besides the Cortex cores in the market. So what is a DSP? It's a combination of a microcontroller and DSP. So that's actually nothing really special. So like microcontrollers, signal controllers have fast interrupt response, control-oriented peripherals, and programmable in C++ language, C or C++. Assembly is not required. Assembly language programming, you did have a chance to play with assembly. Yeah, that was mean for me to force you to do this. Anyway, it was especially so that you can feel then that C++ is pretty nice comparing to assembly. And in case of signal processors, so classic DSPs, it's quite often that you must unfortunately program in assembly and do it in a really sophisticated way, because the assembly language of DSPs is far from being simple. It's really much tougher than the STM8 assembly that you had a chance to play with. So in case of the DSCs, they have microcontrollers like construction, which means that they do have. So it's possible to use simple C++. That's it. Yet. These additional features coming from microcontrollers are mainly from the DSPs. So yeah, here single cycle mux, but I would add here large accumulators. Yeah, sorry, that's not exactly the most important. DMA, cache today, quite often. Plus, we've got a very long instruction word, SIMD instructions. This is becoming more and more common today in case of DSC. So it's not only about MUX, but it's about bar shifters. So the single cycle multiply / divide operations plus DMA plus cache plus very long instruction words, or SIMDs, so it's maybe less frequent. Yet these features, which were classic to DSPs today, we can find them in DSCs as well. Fast execution control, so repeat instructions. They also plus the addressing mode sometimes. Also, sorry, right. So here addressing mode sometimes. That's also. The special addressing, also something that in some DSCs on the market are added to the classic basic microcontroller functionality to form the DSC. So those features are here. Main applications in case of DSCs are not as demanding as for the basic DSPs. So mainly the DSCs are not for communication. Because that's where the major problem is. So there are really gigabit streams of terabit streams of data that need to be processed in a real time, both digital and analog data. If we talk about modulations, or all these OFDMs, so beloved modulation technique today, all this requires really real-time FFTs, IFFTs being calculated back and forth. So this is a heavy calculation. So no, the DSCs are not that fast, so we are not here. Yet they are still, even if not that super demanding application, it doesn't mean that there is no place for signal processing, because it is. Like motor control, like power conversion, like exactly sensor processing applications that we started to talk about in the beginning of today's lecture. Sensor, especially two-dimensional sensors, so which means the cameras, which is becoming more and more common. So neural networking here, so with deep learning and some object recognition, is also the thing the DSCs are used for, the applications. In case of DSC vendors, a couple of them on the market, I would like us to just take those three into consideration today. So besides, of course, so everybody producing Cortex M7 and M4 F classifies to this list. Yet I'm putting aside, so again, as I mentioned, we are stripping out the Cortex microcontrollers, Cortex-based microcontrollers. Let's just focus on something different. So microchip goes first. In case of the microchip by microchip idea of DSC, they have so-called DSP. Yeah, very clever name, as you can imagine. DSP. DSP is a family, 16-bit family, small of small processors with signal processing capabilities. The processors, as you can see, the application here, plenty of possible applications. So sensors, the simple processing of audio, plus naturally motor control, plus power conversion. So, always the same, I would say, always the same. What is inside? And what makes it a bit special? First of all, we've got 40 MIPS core. That's not special. That's not special because it's a standard 16-bit microchip core, which is known from PIC 24H, for example. What is special though is, first of all, wider accumulator. Mark that we've got 16-bit microcontroller, but the accumulator is 40-bit. Why the accumulator should be larger or longer? One of the simple examples, when you have multiply and accumulate instruction, you have a coefficient and a sample. You multiply them together, then you should accumulate such results. Many such results, depending on the size of the filter. It can, if we have a 100-stage filter, then hundreds of such results have to be added together, and then we can only, in order to avoid problems with numerical fidelity, only then we can round up the results and reduce its bit count. Therefore, wider accumulator really does the job, because then we can use 16-bit, for example, coefficient and multiply by 16-bit sample, and then still we have 8-bit space for adding numbers together, which means that we can easily make, in this particular example, more than 200 stages of the filter we can have without sacrificing the fidelity, without the need to reduce the resolution before. It's especially critical, this kind of wider accumulator, if we talk about integer calculations. Then we've got another mechanism which comes directly from the DSPs. Of course, it's a DSP engine. Multiply and accumulate supported instruction. That's special. Then voila, DMA. So wider memory access, definitely an element coming from the world of DSP. And then we've got shadowing registers. Then we've got shadow registers. So then the response to the possible interrupts the response is faster. Thanks to this, we don't lose so much time servicing some peripherals, and the processor can spend this time saved years on processing data. In case of the peripherals, standard set of peripherals, the amount of RAM pretty small. So actually, that's it can be seen that this 16-bit microcontroller, because those values are not really satisfactory. Besides, we've got rich peripherals theoretically. Okay, nice. So we've got audio DAC, we've got control DAC, we've got 12-bit ADC, but we've got only 12-bit ADC available. So not to the result. This actually resolution is nothing really super special. It's just okay. It's just fine. But what we're missing here is we are missing in those peripherals the port for DRAM, for example. In case of signal processing, we need a lot of RAM usually, so it's pretty common. So here 30 kilobytes, up to 30 kilobytes of RAM, and the lack of DRAM interface is a negative feature, but still, this is a processor that costs, yeah, take a look, QFN28, few dollars, really, a few dollars. Yeah, there are two versions, DSP30 and 33F. They are still pretty interesting from practical point of view. Another important family, I think even more important from practical point of view, is the family delivered by Texas Instruments. So the Texas Instruments was trying in the past to go to A, so to simplify the DSP and to form this DSCs coming from simplified DSP. It was family C5000. Which the market didn't like at all, and then they introduced some microcontroller with extra DSP features, and that's actually what the market thought useful. I'm saying about the family of 28XX or XXX because it's a family with a lot of digits after 28. Three major families now: fixed point series, Piccolo series, and Delfino series, and there is the Concerto, so even fourth, but the Concerto is a bit tricky because we've got the in the Concerto line we've got the Cortex microcontroller, so tricky, not tricky, but then we've got a heterogeneous processor structure with Cortex M4 and with the 28XX core. The family, so we have a lot of really, to be honest, it's quite abundant family. So it's not that we've got just a couple of devices like in the microchip portfolio. Here there is really a substantial number of devices available in various shapes and sizes. All of them are 32-bit because the core itself is 32-bit, but they exist in this family the devices with multiple cores. Difficult to use. So it's Texas Instruments. So in Texas Instruments, nothing. It's simple. But still, in the next gen here, so because it's not up-to-date slide, to be honest, I do apologize for this, but there is in the next generation, they are really interesting multiple core solutions with special peripherals for supporting the calculation. So up to 4 cores, up to 1000 MIPS. In general, the processors are not, with taking raw performance into consideration, they are not as fast as Cortex M7. So Texas Instruments is still having some problems with it. Still, what is excellent here is that the core itself is having a lot of features coming from the DSP world. So that Texas Instruments has always been an expert in signal processing, and for example, in those cores, we've got a lot of addressing modes coming directly from DSP world. There is no support for butterfly addressing or for circle buffer addressing. Okay, that's true. But there is a support for fast data transfer, for example, fast data access through different memories. So very interesting. Many interesting features here as well. There is a support for control law calculation. So there is so-called CLA, control law accelerator, which means that we've got in these processors, we've got special programmable peripheral, because that's how we can classify. It's not another core, although it looks like, but it's a programmable peripheral block where we can use it. So programmable, but it's interesting from this perspective, the CLA block, because it's sometimes we've got programmable logic inside the microcontroller, which means that we can change the connections inside and have the block as a use the block as a glue logic for connecting external signals to a microcontroller with functionality tuned to our needs. In case of CLA, the idea is here that we can have a block that works with input and output, so just processes the data. So let's say micro DSP, because it's only for processing data in a particular way. And then which way does it process the data? You do in C, not in VHDL or Verilog, so not in hardware description languages, but you do this functionality, you modify this functionality writing in assembly language. Unfortunately not in C, but in assembly language. So there is some difficulty in programming this. Again, so Texas Instruments see this comment, but it's working. So you can make some, you can basically prepare some extra peripheral working as a coprocessor, delivering your working initially, preparing the data for further processing in the major CPU, increasing the overall performance of such a DSC in real applications. Therefore, the lower clocking, as we talk here about in the Piccolo line about the clockings comparable to M3 processors, and in Delfino line, we can count on clocking usually in the range of Cortex M4s, so not super outstanding clock rates, and therefore raw performance not extremely exceptional. Yet these architectural nuances they help to deliver really decent and really good performance coming from this DSC, from this Texas Instruments DSC devices. So Piccolo, fixed point, and Delfino line here with also what is interesting here are the peripherals. Non-negligible thing, the peripherals which are tuned especially for signal processing. So they are not tuned for some control applications. Okay, you can use it for control applications, but especially for signal processing. So take a look about this. The processor from Piccolo series, so small processor. So okay, we've got small clocking. We've got not too large memory, 64 kilobytes is nothing. We've got tiny package, so just 38 pins, but we've got those features. So take a look, 150 picosecond enhanced PWM, so very high resolution, 150 picoseconds. It's 8 gigahertz equivalent PWM, so excellent PWM, really excellent. We've got 5 mega samples, 12-bit ADC, which means that we can use this simple, trivial, let's say cheap microcontroller for processing of pretty complex analog data. We've got on-chip oscillators, we've got comparators, we've got high-speed DAC, not ADC here, but that's DAC, and some standard stuff. So interesting, really interesting peripherals in these processors. We can find in this processor, we can find with the performance going up with the Delfino series. So Piccolo is slow. Delfino series starts to remind Cortex M7 more or less, something between M4 and M7. Yeah, it's interesting observation of this competition. So this Texas Instruments portfolio, in contrast to Cortex portfolio, so Cortex processors. Basically, Texas Instruments it's not on the top, so it was earlier on the market than Cortex microcontrollers, and now it's slightly behind, but they are trying to catch up. To be honest. Yeah, and to finish this this subject, Freescale, so DSCs by Freescale. So a bit historical, to be honest, a bit historical, even more historical, because Texas Instruments is still fighting. In case of microchip, they are vital part of the whole product line. Those DSPs. In case of Freescale, no, it's NXP, to be honest. Freescale had a lot of history with being Motorola before, and leading the world of processors. Now it's trailing the world of processors. Yet there is such a thing as the word DSCs, and you can still find in the market a lot of signal processors coming from Freescale and coming from NXP now. So this was this family, so 56F, 8, and then a few digits, so here is as well in upper mid and mid scale. So digital signal controllers, again supporting the multi-plane accumulate constructions, but these families, today comparing to what we can expect today, not really extremely fast. So even lower range than the Texas Instruments that I tried to show you just a few slides before. Still, you can find it. I wouldn't recommend actually using it as they don't have anything really extra special to comparing to standard Cortex families, or to even this Texas Instruments portfolio, or even to this DSC by Microchip. So DSP, which is nice because it's small. So if you need something really tiny and small and cheap, then why not DSP? Still, there is something like this. So if you want, you can really try. And to finish this subject, a few examples, a few use cases. So we're talking about the use cases of, for example, SMPS, so switching DC-DC converter, DC-DC switching converter, and where is the space for DSCs there in such a SMPS? Here we can see, for example, a simple schematic showing us the AC input. Then, of course, we've got the first rectifier, so we've got the DC here, and then we've got the bridge with the conversion transformer, and then the rectifier again, delivering the output. All this is controlled. All this required some control. Here, the first microcontroller here is used for power factor correction. And that's why it measures the phase and it drives the transistor here, and all this has to be done. So take a look. We've got three here, three conversions. So measuring the voltage and the current, and then the voltage again. And depending on this, we've got current and voltage regulator, and we'll modify the duty cycle. So we change the phase, correct the phase. Now with the Q1, so this is only the phase controller. The control is done through the second processor, which measures the output, and depending on the output, actually drives through the PWM, drives the bridge, and changes the duty cycle of the conversion. Theoretically, a simple thing. That's why we don't need always very complex DSCs to do this job, and that's why DSP, why not in such an application? Not such a bad idea. Another sample application, so digital dimmable light ballast. So if we have headlamps, so the discharge lamps, they need special ballast for operation. Otherwise, the plasma is unstable. So for effective operations, these lamps are used, for example, as a UV source. Still, despite having LEDs, we're using some HID lamps. And again, for this ballast, we need to control the voltage like here, the current flowing, and depending on the voltage, here's exactly the PFC correction, and here we have the ballast itself. The ballast itself, there is a measurement going on with that. Checking if there is everything operation is going well, if the current flowing is fine. Again, real-time configuration, real-time operation required because the data come from the sensors all the time from the measurements, and then the response with the driving of the transistors. Then another standard subject for DSC controllers today. So the control of the three-phase motors, very popular motors today. So the so-called brushless motors, because they can be very effective. They can be very effective in case of torque, in case of efficiency, and besides they can be easily. They are small, they are light. And they're reliable over a long time. So everybody likes today to use three-phase motors driven from DC, because take a look, we don't use three phases, but we've got DC here as an input. And then the DC itself, we have to use bridges because that's exactly what's hidden in this module. So we have the bridges in this module. Of course, here in this integrated power module. So then we have the H bridges here, three H bridges driving the L1, L2, and L3 lines. And then the processor not only has to drive the lines, but more importantly, it has to measure the current flowing through the windings. So this is really complicated task normally, because we drive the lines. So depending on the configuration, but in general, we drive it with a PWM signals, and we need to measure in a particular time moment. So in order to be able to find out where the motor is and which phase should be driven in what way, so there is they are pretty complex and pretty heavy math included here, with all the transforms of Park and Clark and some others. So this really requires operation, and driving on the phase motor requires this processor putting aside filtering problems or some FFT calculation, just about calculating the current or the PWM duty cycles here. It takes really quite a lot of time. Besides, there is, as you can see, some corrections you see. So as well, the additional task that needs to be done. So DSC here, excellent application. DSC here, an excellent application. And the last use case, here for the DSC, battery-powered wireless sensor. Battery-powered wireless sensor. Again, an example that we have a battery. We have a modem here. So of course, this is pretty ancient today. So modem, but general idea today is that we take the STM32 WB or WL with the small integrated in one structure and Cortex M4F as the major core, and then we are having sensors, and then we condition the sensors and send them over the wireless interface to the world. That's also the application theoretically for microcontroller, but because we've got the sensors here and we need to process the sensors, then the DSCs can be used for this purpose. Good. So yeah, there is a chat. They are bootstrap here. in case of the schematic, but yeah, it's not a complete schematic. That's the response to the question. So normally, because we need to first we drive the lines, then we need to measure it, the capacitors. I don't know if in this configuration they were not to measure to have a connection for measuring the current flowing through the voltage at the windings. To be honest, I'm not sure about the schematic because it's just a very simplified schematic. So I'm not sure what the capacitors are really for here, to be honest. So it's just about guessing. Any more questions? Because yeah, that would be it that I wanted to share with you about the DSCs. We have still a couple of minutes, but we will start a new subject. The new subject is because we have last 2 lectures actually left. If next lecture is off, so it is we are getting back to programmable logic, so to FPGAs and the programmable programming language of the FPGAs, so the description language of the FPGAs. So I didn't want to start it because then we'll have 2 weeks break. So that would be it for me from today. As of today, any more questions maybe about this, about the DSCs? If not, my last comment maybe about the DSCs is that today it's pretty difficult sometimes to discern a DSC from a microcontroller, unless it has a special name like DSP. So there is a DSP, it's different than PIC24F, but in case of Cortex-M4 especially, they have features. They share a lot of features from DSPs, which means that we can classify any Cortex-M3F processor as a DSC, but yet they are classified as microcontrollers. Even Cortex-M7, which ticks a lot of checkboxes about the DSPs, is classified as microcontrollers very often and not as a DSC. So today, DSC and microcontroller is really difficult sometimes to discern. Yet, formally, we could still think about DSC as a slightly different category, where we could classify the Cortex-M4F, Cortex-M7, Cortex-M33 applications, processors, plus DSPs, plus the Texas Instruments 2800 family, plus the 56F8 family of the former Freescale. That's it for me for now, for today. If no questions, thank you very much again. So now no lecture next week, maybe in a bus. So see you in a bus next week. Have a nice day. Bye bye.